In this project, we investigate the self-piercing riveting joining technology. SPR is particularly attractive when other joining methods are not viable, like is the case for certain aluminum welding. SPR forms a mechanical joint between two thin plates in a four-stage process: clamping, piercing, flaring, and releasing. Our goal is to introduce microstructure to SPR simulation through data-driven mechanistic modeling. Up to now, the SPR process has been primarily studied at the continuum scale, where material microstructure evolution is ignored. However, modern materials have tailored microstructures to achieve desired results, making the final microstructure state in the plates critical for joint performance prediction. Our primary goal is to use multiscale modeling to investigate the SPR process with real-time microstructure evolution history. The methodology laid down in this work shall pave the way in building a process-structure relationship for the SPR process. The SPR model contains the 6 parts shown. The geometry is given. The holder and die are fixed in place. The punch is displaced 8 mm in the negative y direction, causing the rivet to move. The plates make up the multiscale region. In this region, microstructure responses at each integration point in the microscale finite element are computed by RVEs. The RVE replaces traditional material laws and provides detailed microstructure evolution. To allow the rivet to penetrate through the metal plates, element erosion is activated in the model. The element failure is predicted by the RVE calculation. Note that we designed the element erosion zone to minimize the mass loss when using element deletion. Only RVEs within the element erosion zone will compute microstructure damage and RVE failure. Material parameters for the aluminum plates and steel rivet are given. The non-concurrent model uses the built-in ductile damage model provided by ABAQUS. Here, the plastic displacement at failure and evolution function must be defined. Our concurrent model bases damage on the effective plastic strain. Once the RV damage parameter surpasses the threshold, the element will fail. Our method equips ABAQUS with real-time microstructure evolution enabled by SCA. Prediction of the microstructure damage and failure process is directly done by the RVE. Here are our results. The rivet comes down and penetrates the top plate. The rivet then proceeds to penetrate the bottom plate. Flaring begins to occur and the interlock between the rivet and plates is formed. After the SPR simulation is completed, the multiscale framework presents the macroscale von Mises stress evolution as well as the microscale RVE von Mises stress and damage evolution. Here we plot the Mises stress for two selected elements. One can see the stress accumulation around the inclusion matrix interface region. This leads to damage initiation and subsequent failure of the RVE. Here we plot the Mises evolution in the two scales concurrently. The top circle corresponds to the initial position of the RVE on the right. It fails within the first few frames. The bottom circle corresponds to the RVE on the left. It fails as the rivet begins to penetrate the second plate. Here we plot the reaction force of the multiscale model. We also plot the reaction force when the ABAQUS built-in damage model is implemented. When comparing to experimental data, the multiscale model underpredicts the reaction force due to element erosion. This can be mitigated in the future using a meshless method or a multiscale model with an adaptive mesh scheme. We've shown how to explicitly incorporate microstructure in the SPR process. We've developed an efficient, real-time concurrent multiscale simulation in ABAQUS. The analysis shows how the impact of the microstructure can be important in designing the SPR process.